Hello all. Today we will discuss about the fundamental operators in vector calculus used extensively in electromagnetic waves, that is gradient, divergence and curl. So these operators help us to understand the physical quantities like electric potential, temperature, electric field, flux vary in space. So overall, we will be discussing about gradient of a scalar field, divergence of a vector field, curl of the vector field and their mathematical expression, physical interpretation of the equation and application in different coordinate systems. The first one is gradient of a scalar. The gradient of a scalar field V is defined as the maximum rate of change of V with respect to the space, where V is known as the field. Mathematically, the gradient of V is written as gradient of V equals del operator applied to the V. The result of the gradient is always a vector even though V itself is a scalar. So in Cartesian coordinates, the gradient of scalar V is given by gradient of V equals dou V by dou x in x direction, dou V by dou y in the y direction plus dou V by dou z in the z direction. So each partial derivative represents the rate of change of V along that axis. So here dou V by dou x is the variation along x axis, dou V by dou y is a variation along y axis, dou V by dou z is a variation along z axis. So the gradient vector points in the direction where V increases the fastest. So if we consider V as electric potential, then its gradient gives the electric field direction. If V is temperature, the gradient points towards the direction of maximum temperature increase. Thus, the gradient equation converts a scalar field into vector field that describes spatial variation. The next one is divergence of a vector. The divergence of a vector field A is defined as the net outward flux per unit volume at a point, which is given by integral closed integral of A dot ds. So the divergence of A at a given point P is the outward flux per unit volume as the volume shrinks about P. So mathematically, divergence is written as del operator dotted with vector A. So the result of divergence is always a scalar quantity. In Cartesian coordinates, the divergence of vector A is given by dou Ax by dou x plus dou Ay by dou y plus dou Az divided by dou Z. Here Ax, Ay and Az are the components of A along x, y and then Z axis. So each term represents how much the field spreads along that direction. If the sum is positive, the point behaves like a source. If the sum is negative, it behaves like a shrink. So the physical interpretation of divergence is that consider an electric field around a charge. Positive divergence indicates a positive charge acting as a source. Negative divergence indicates a negative charge acting as a sink. So zero divergence means the field lines neither originate nor terminate there. Hence, divergence tells us whether a field is diverging or converging at a point. So in cylindrical coordinates, del dot A is equal to 1 by rho, dou by dou rho, rho into A rho plus 1 by rho, dou A phi divided by dou phi plus dou A z divided by dou z. In cylindrical coordinates, the divergence equation changes because the geometry is different. The expression includes radial component, angular component and the axial component. The presence of the radius term accounts for the fact that area changes with radius. So this form is useful for analyzing current flow in wires, coaxial cables and cylindrical waveguides. For the spherical coordinate system, del dot A equal to 1 by r square dou by dou r square ar plus 1 by r sin theta dou by dou theta into a theta sin theta. plus 1 by r sin theta dou a phi divided by dou phi. So here the spherical coordinates divergence includes radial variation, polar angle variation and then azimuthal angle variation. So this equation accounts for how flux spreads over spherical surface. So it is commonly used in point charge fields, radiation problems and then antenna analysis. The divergence theorem states that the surface integral of a vector over a closed surface is equal to the volume integral of its divergence. So which means that instead of calculating flux through the closed surface directly, we can integrate the divergence through the enclosed volume. So this theorem forms the basis for Gauss law in electromagnetics. The next one is curl of a vector. So curl helps us understand the rotational or circulating behavior of a vector field. It plays a key role in electromagnetic theory, especially in Maxwell's equation. The curl of a vector A is defined as the circulation of the vector field per unit area as the area shrinks to zero around a point. Mathematically, curl is written as curl of A equals del cross A. Curl of vector field is itself a vector quantity. Curl indicates the tendency of a vector field to rotate about a point. If the curl at a point is zero, the field is said to be irrotational. If the curl is non-zero, the field exhibits rotational behavior. So if a simple physical analogy is a rotating field or whirlpool. So the direction of the curl vector is given by right hand rule. If the fingers of the right hand follow the direction of the circulation of the field, the thumb points in the direction of the curl. Thus, curl gives both direction of rotation and strength of the rotation. So in Cartesian coordinate system, the curl of a vector A is expressed using a determinant involving unit vectors, that is ax vector, ay vector and az vector, and the partial derivatives like dou by dou x, dou by dou y, dou by dou z, and vector components like ax, ay and az. So each component of the curl corresponds to the rotation in a plane perpendicular to that axis. So the x component of curl represents the rotation in the yz plane. Y component represents rotation in zx plane. Z component represents rotation in the xy plane. If the curl component is large, it indicates strong circulation in that plane. Whereas the curl in cylindrical coordinate system expresses the change due to circular geometry. So the equation includes radial component, angular component and axial component. So this form is useful for analyzing magnetic fields around current carrying conductors, coaxial cables and then waveguides. And then in spherical coordinate system, the curl equation accounts for radial variation, polar angle variation and azimuthal angle variation. This system is commonly used for antenna radiation and electromagnetic wave propagation. So in electromagnetics, curl of the electric field explains electromagnetic induction. Curl of the magnetic field explains current flow and displacement current. So these relationships are actually the part of Maxwell's curl equation. So the importance is that these equations are extremely important because gradient relates potential to electric field, divergence relates electric field to charge density, curl measures the rotation of a vector field. So this appears directly in the Maxwell equation. So thus in order to summarize, gradient measures rate and direction of change of a scalar, divergence measures spreading of the vector field, coordinate system help apply these concepts to practical geometries. So these equations are foundational for electromagnetic wave analysis. Curl measures the rotational behavior of a vector field and it is a vector quantity also. So direction is given by right hand thumb rule and curl is essential for understanding the electromagnetic fields. Thank you.